Okay, so now I'm going to discuss about one more antigen antibody reaction test. It's a different type of test. It's called immune assay. And this particular immune assay, here we are using some radioactive molecule as a signature molecule. So this particular immune assay known as radio immune assay or RIA. So particularly RIA was introduced by the two scientists, Barsham and Yellow in 1959, and they have done this particular in vitro assay for detection of insulin in human plasma. So it is also a serological test, serological method based on immunological antigen antibody interactions. And here it makes use of radio level substrate to measure the trace amount of hapten. Hapten means it may be drug, molecule, hormones, steroids, antigens, whatever be the molecules that is present in a serum in very negligible quantity, very negligible amount. And this particular type of haptens of the biological samples can be, a trace amount of biological samples can be detected using this radio level immunoassay method. And this particular method is preferred when the trace quantities of the substrate is difficult to trace, is difficult to measure by using the other alternative analytical techniques. So we can use this particular type of immunoassay that is called RIA. What is the basic principle of RIA? The basic principle of radioimmunoassay is nothing but competitive binding of the antigen and the antibody. Here competition is going on between the unlabeled antigen and the labeled antigen, or radio level antigen. And this radio level antigen we call as trace molecule, and this tracer will compete with the unlabeled antigen for a fixed limited number of binding sites on the specific antibody or receptor binding sites. So this radio level antigen that are expressed here as Ag star, so competes with the unlabeled antigen, and this labeled antigen are expressed here in blue dots, and the unlabeled antigen that is a patient serum that is expressed here in yellow dot. You can see that the radio level antigen or the tracer competes with the unlabeled antigen, patient serum, that contains the unlabeled antigen for the binding site of the fixed amount of antibody. Here this Y-shaped, orange color shape is the antibody. So prior to the test, what we have to do better to say, what first we have to label, or we have to complex with the antibody, antibody along with the labeled antigen, is radio level antigen. Then we have to start, we have to check it first, means how much amount of radio level antigen is needed to, to neutralize all the sites, all the binding sites present in the required amount of specific amount of antibody. That we have to detect prior to the test. Now we have to go for the actual test, where the first test we have two components. One component is a specific concentration or specific amount of immunoglobulin and the radioactive. And from this prior test, we can get the idea what amount of antigen is required for the complete neutralization of the antibody, that is to complete the binding site of the fixed amount of antibody. Now, the actual test begins with the three components. And what are the three components? One should be the specific amount of antibody. Second one is your level antigen. And the third one is a patient sample that is believed to have the unlabeled antigen. Now we have to go for the test. And then here you can notice the competitive inhibition or competitive binding between the two antigens, level and the patient's or the unlevel antigen, means the blue and the yellow spots. So the yellow spots will also bind, and that particular spot we can have the labeled antigen that should be unbound instead, and that unbound antigen we have to look for. So we can say that okay, this much of unbound antigen is present there in my sample, so this much of unlabeled antigen has bound with the antibody. So here you can see the radioactive antigen. This is the stressor and the primary antibody. Next, we have to add the unleveled antigen. In this left-hand side, the picture you can see the leveled one is a red one, unleveled one is a blue one, and here you can see here you can see a mixed, means the radioactive antigen displaced is displaced by the unleveled antigen, and then you can have in your solution both the unlevel and few amount, means mostly the level, and a few amount the unlevel. So radioactivity of the supernatant, that is the free radio level antigen or free tracer, we have to identify, we have to detect. So we have to detect the radioactivity of the supernatant, not the packet. So here the unlevel antigen will bind with the antibody and will replace the leveled antigen. So the amount of leveled antigen that is present there in the solution in unbound condition, and that should be present in the supernatant. Now what we have to do? We have to use a secondary antibody. This secondary antibody we can use for precipitation reaction. So this secondary antibody will bind with these primary antibodies, and then we have to go for centrifugation. So during to this centrifugation process, now the secondary antibody will bind with the primary antibody and will drag it at the bottom of your centrifuge tube. Means you can get now the precipitate, and the precipitate contains secondary antibody, primary antibody conjugated with unlabeled antigen and maybe few amount of labeled antigen. So in your supernatant, you have your free tracers in the level antigen. So that level antigen in your supernatant, there we have to identify, we have to determine the concentration or radioactivity of the supernatant there. So what are the instruments we need? We need 2 to 3 instruments. First is centrifuge. So for separating the bound radio-level antigen and the unbound radio-level antigen, we need to go for centrifugation. For that purpose, we need a centrifuge machine. And the second one, then we have to separate the supernatant from the pellet or precipitate, and the supernatant radioactivity we have to check. For that purpose, we need either scintillation counter or gamma counter. If we are using the radioactive isotope, that is indeed a beta emitter, from we can get the beta emission. So for that purpose, we have to use scintillation counter. And if it is a gamma emitter, then we have to, means if it is iodine isotopes. If it is carbon or hydrogen isotope, then simply we can go for scintillation counter. If it is iodine isotope, then we have to go for gamma counter, because here we can get the gamma radiation. So these are the instruments we need for this purpose. And what are the requirements here? The requirements are, first is the antigen, and the process antigen, means that is unlabeled and labeled antigen, radio labeled antigen, then specific antibody and secondary antibody. And the third one is a standard HOP. It's an already developed assay system. So if we have, then we can go for preparing and radio labeling of the antigen. So radio labeling of the antigen can be done by using platinum, by using C14, by using iodine 125. So any of the isotopes we can tag with the antigen first. Then we can remove the untagged antigen, and then we are using this tagged antigen with specific amount of antibody. So development of the assay system, first we have to separate of the unbound antigen from the mixture. This is very crucial step. Means before your actual experiment start, you have to perform this process. And you have to ensure that you have isolated, you have eradicated the unbound antigen. Only in your sample you have the radio labeled antigen or the pre-tracer antigen here. So this achieved by binding the antibodies to the microtiter well surface. This is a solid surface or solid phase for RIA. Then antigens bound to the fixed antibodies remain stuck to the inner surface. You have to decant it, wash it multiple times, the microbials, to remove the unbound antigen. And you can have other techniques like separation using centrifugation, but mostly people are doing this particular reaction in microtiter plate. So simple decanting and washing multiple times can remove the unbound antigen. So this is the overall assay procedure. First, you have to add known amount of your test sample, then radio level antigen to the microtiter. Then you have to incubate it, allow the reaction to complete, decant it, and wash it multiple times. The content of the well and all the unbound antigen will be removed. Then radioactivity remaining in the microtiter well is measured by either the GM counter or the scintillation counter, gamma counter. Then intensity of radioactivity is inversely correlated with the concentration of antigen present in your test sample. So this particular method is very sensitive, highly sensitive, so very low concentration of antigen present in your patient sample can be determined. So highly specific reaction, or it's very sensitive. Now what are the applications? So this particular test can be used for assessment of drugs or drug abuse, like digoxin, like digoxin, then flurazepam, then hydromorphone, and then hydrocodone, LSD, morphine, etc., etc. Then analysis of vitamin like riboflavin and folic acid present in blood sample. Also analysis of hormones like aldosterone, testosterone, etc. can be assessed. Blood bank screening for hepatitis B surface antigen, if it is present there in very trace amount, and also it can be assessed. So in blood bank it can be used. The early detection of cancer and tuberculosis, this particular method can be used if we can identify a particular antigen. In testing the functioning of thyroid gland using iodine 137 to contrast. In the diagnosis and treatment of peptic ulcer, thyroid disorder, this particular test is very handy in determining RBC volume and the whole blood volume you can do this. So what are the merits and demerits? So merits are this particular test is reliable and reproducible, highly specific, highly sensitive, it's simple, rapid, precise, accurate, and very less amount of sample we need, very small amount of sample, 5 to 50 picomole per ml sample can also be traced. And the versatile use. So in case of antibodies, drugs, metabolites, hormones, nucleic acid, proteins, viral antigen, vitamins. So in all sorts of cases, very negligible amount if it is present there in your sample can be traced, can be detected. So it's a versatile, it has a versatile use. But although it has some versatile use, it is highly specific and sensitive, still it has some demerits. The first thing is that we need a sophisticated instrument like GM counter, scintillation counter. These are very costly instruments. And the second thing that is more process is your radiation hazard. So we are using here radio level reagent. So to keep the radio level reagent, to use the radio level reagent, this is, you have to take very precautions, and also you cannot throw it everywhere. So requires skilled personnel and is an expensive process. So laboratories require special license to handle radioactive material, and also require special rearrangement to keep and store this radioactive material, and also this radioactive waste disposal, as I said. So that is why this particular method has some demerits. But if your laboratory is well equipped, if your laboratory has all the facilities, then definitely you can perform this test. Thank you.